Yeah, welcome to lecture number 9 in parallel distributed computing. Today we are talking about vector extensions on your kind of usual CPU or Intel CPUs. Yeah, so it's about AVX. That's also a part of parallelization that we can use. AVX is a vector extension, or the possibility or the ability of your processor to actually do vector calculations intrinsically. It is possible that if you write a clean code, that your compiler actually does this automatically if you set the appropriate flags, and then you do parallel computing without actually knowing this. But if you want to force it, you have to use these so-called intrinsic vector operations that we'll have a look at today. We go through the example of a matrix multiplication, also talk about memory allocation today a little bit. So, in order to follow this one example that I have, please go to my folder here. So okay, start up your computer, because we learned that this takes a lot of time. Yeah. So start up your computer and go to this PVR 2025 Gaia, and then lecture 9. This is the lecture of today, and make a copy of this matrix multiplication into your own folder, and also please take the job file that is located here. I recognize that I'm always running the simulations on the login nodes, which I told you please don't do it, but for demonstration purposes this is often more convenient, but this is not a very good idea. So we are only doing this because we use only a few seconds of simulation. When you do your homework, please use job files and running on the queue, not on the login node. And by the way, Phoenix is an old computer. It has only one working login node left. So when you do a simulation there, you're really causing trouble to everybody else. Okay, and I'm the bad guy always presenting this. Yes, so about the so-called advanced vector extensions, AVX. So there have been previous vector extensions. I think they were called MMX. That have already been around in the 90s. So AVX has been introduced in 2008, where it allows you to use 256-bit floating point operations. So we make vectors. So for example, we can use 8 single precision float operations, or we can also use 8 integer operations. So from the handling of them, they are very similar. The example that we use today will just use integers. In 2013, there was AVX2 that also uses apparently also int. int 32, so integer operations were added. I hope all of this here is correct. There was in 2016, there was a further extension where we can use 16ths of these. So we go to 500. So we have broader vector registers. Now, history of Phoenix. Phoenix is 10 years old, so then you see Phoenix is too old for having this. You can look up whether you have AVX with this command here. Somebody wrote this. So I'm a stupid guy. I'm not good at using Linux. Yeah. So, but apparently this is the command that you have to use grep -o. So you look for things that go with AVX in the proc CPU info and sort this somehow, and then you see that we have an ability to run AVX2. I'm wondering why we don't see AVX. Okay, so we also have AVX, but we don't have AVX 500. No, we don't have AVX 512 in it. Yeah. So Phoenix is not able to run AVX 512. So for this purpose here, okay, so you always have to, when you go learning something in the university, if you're out of university, you already know it's old stuff. So this is why we try to just teach the concepts, and then you have to go on and go to the next level yourself. Yeah. So we are back in year 2013. Yeah. You know, in this time there were much less trouble in the world. Let's think about these times. So what we can do is we use these data types. They are called here __M256. So this means there are 256 bits in which, for example, would be 8 floats or 8 integers. There is also the possibility to use 4 doubles, and they now would be stored like this. So I'm indicating 1 byte here as 8 bits in this. I hope, yeah, 32 bytes. Oh, okay. Okay, I got here the wrong color. This, of course, is also bytes. Yes, sorry for the wrong color. Bytes, 32 bytes. Wait. AVX need to be aligned. Okay, yeah. So, okay, sorry for the wrong color here. AVX vectors need to be aligned in the memory boundary by 32 bytes. In the next level, they have to be aligned even further by 64 bytes. So this is such that you can read them in one go. Yeah. So they cannot be anywhere in the memory, but they have to be located in such a way that you can read them in one go. And this, for example, means that so the least significant bit, the last 5 significant bit of your address have to be 0. Yeah? So you cannot start from any address, but only from an address that you can divide by 32. So this is something that we have to take into consideration when we use them. Okay, so what we have to do is kind of two things in order to run this, or to make this run. So this is inside the C standard we can use this, but we have to include a header for the intrinsic functions. So this we have to include here all the time. And we also have, when we compile it, we have to set a flag for the compiler -m AVX2. Yeah? So obviously we don't want the code automatically to use AVX, because AVX is not compatible with the standard x86 standard. So because there are, I mean, maybe nowadays all the computers have them, but there were computers before 2013 and they don't have them, yeah, or even newer computers may not have them, and so you don't want it always to be used, but you can tell them to use it. So when you compile this code this way and you run it on a different computer, it may not run, yeah, because your different computer may not have vector abilities. So it is unfortunately not pretty to use this. So let's look at this example here. So let's have a function that is add two vectors. So we get in here these vectors, vec A, vec B, and A, B, and C. And now we want to split this up and make this vector product. I guess C is the vec C. No, it's not a vector. Okay, it's not a product. We are adding vectors, so we get out a vector. It's a vector plus vector. Yeah. So these vectors here, or actually the arrays here, they are not necessarily of the size of the vectors that AVX can use. So we still have to loop over these vectors, but we loop over this vector by increasing the counter by 8 now. And in this simple example, we assume that we can divide n by 8, right? Otherwise, we would have to do a refill here. So now in order for this to work, first we have to load our data into a vector. So we'll have this thing of data type __m256, yeah, vector ABC. So we load from the address of A and from the address of B. Then we do this calculation. By the way, not the address from A starting from I, yeah, not from the beginning of A, but A. So this counts up the array, yeah. So and then we have to store. Then we can do the calculation. So this is simply add packed single, PS packed single. We add these two vectors and then we store this at the address of CI in the C vector. Yeah? So we do 8 additions in one go instead of doing 1 addition in one go. But what we have to do is we have to load these into the vectors and then we have to store them again. Good morning. Okay. So, and this is, I mean, you are not able to just say vector A plus vector B. Yeah. So you have to use this strange intrinsic function, which makes your equations look a little bit ugly. So you don't just have the operators. Yeah. So you always have to go through these strange things here. So we need to understand how this loading goes forward and backward. Now, in this slide here, we are assuming that the vector is already continuous in the memory, so that we just can load a chunk of memory into this array, into this M256 vector. Now there are different ways of doing this, depending on what we want to load. So here we want to load packed single. So this is expecting a float with an address. And this here means unaligned. So we do an unaligned read. So I just told you that the vectors on which we can do the vector operation, they need to be aligned. Yeah? So, however, here, the data that we load into the vector, because this is actually a copying function, this is not necessarily aligned. So we can tell it that now the data that comes is not in this alignment with the memory. Yeah? And then it can take this non-aligned memory, puts it into an aligned vector on which it then can do the calculations. So this is indicated when you write here this U. If you don't write this U, it will assume that the memory is already aligned here. So I guess the difference why we have this and this is, I mean, this here must obviously be faster. Yeah. So if your memory is already aligned, so I can just put the cache line where it's supposed to be. So this loads 8 32-bit floats from aligned memory. Yeah, sorry. Right. So this is a single SI means signed integer. So here you get an integer address. So if you do an aligned read, the 5 least significant bit of the memory address must be 0. Yeah, otherwise it's not aligned. All load and store statements exist in aligned and unaligned versions. So we always, you see whether it's unaligned, then you got a U here. Aligned is without this U. This is packed double, so what you have packed single, you have assigned integer, I guess you have also unsigned integer, and then packed double is for double. So this stores 464-bit floats, in this case to unaligned memory, yeah, because there's an U here. Okay, arithmetic instructions. So as I said, you don't just write plus and minus and say you always have to use these ugly functions. Yeah. So the first one here is doing this is a single So we are adding singles. Yeah, I mean, as you see, we have only one data type for the for our vectors, right? Which means that every time you do an operation, you have to tell the compiler how to interpret your data. So if you previously loaded singles into this, you also have to, the compiler has forgotten that you loaded singles. You have to tell them, now we add singles, yeah? And here you multiply singles. You can subtract singles, you can add singles, and then with the integer it becomes even a bit more complicated when you multiply integers. So when you multiply integers, their range usually doubles. I mean, if you don't want to run into overflow. So, which means that if you give in 32-bit integers, what comes out is 64-bit integers. So you give in 8 small integers, you get out 4 larger integers. So this is usually not necessarily what you want to do. Therefore, we also have this mullo function, yeah, where you map 32-bit to 32-bit, where you just take the lower 32 bits of your operation. So if you run into overflow, they will be chopped, the head will be chopped off. Yeah? So then there are plenty of other instructions and instructions of the type of computation, for example, bitwise logical functions. And of course, they are shuffling and storing. So, what is it? Gather functions. Okay, I don't have an example for gather function today. No, I don't. Yeah, but you can also. So gather means you can give an address map. Yeah. So that it picks data from different parts in the memory, different spots in the memory, and packs it into a vector. That would be a gather. Then there's also the opposite, a scatter, which I believe is not part of AVX2, but it is part of AVX 512. Yeah. So. But gather is a function in AVX2. Okay, now there is a strange thing that I learned only yesterday while trying to prepare this lecture. I have to admit I'm probably not the best guy to teach AVX, because I'm not an expert of AVX, but it's part of the curriculum, so I have to teach AVX. So we are learning together, okay? Yes. So there may be some things that are a bit confusing, and I'm not sure that you heard about this concept of little endian and big endian. Okay, give me a hand. Who knows what is the difference between little endian and big endian? Okay, so we have 1/3 has this experience. Okay, so this is kind of a little bit like riding on the left side of the road or riding on the right side of the road. Yeah? Basically, the way you can store your data you can store your data in 2 different ways. So the way you as a human being would write down a binary number would be big endian. So you would put the big in your writing direction, whatever your writing direction is, and I assume that now, okay, European writing direction, we go from the left to the right, yeah, in Latin. So we put the largest digit to the front of the number, and the smallest digit to the end of the number. So we start with the big end. And this is the same way you could store your data in big endian format. So for example, if you store the number 4 in this in 1 byte, so this would here be a char, right? In 1 byte, then you would write this as 00000100. That would be 4, and this here would be 3. I hope this is visible to you. So all of zeros and the last 2 are 1. Yeah? So this is how you would write this down, because you are a human being would write big endian. But obviously you can do this the other way around and write the least significant bit first. And this is called little endian. So now obviously you can build computers in these 2 different ways. And different computers have been built in these 2 different ways. And there's a lot of historical reason behind this. Yeah? So actually these processors that we are using here, so they were among the first that were used in the first place. So the x86 from Intel, yeah, they used little endian. But this is not the only possibility. There's also something that's called PowerPC, Motorola, Motorola 6800 type of processors. Were also very common, no longer so common nowadays. It's ARM. I don't know what ARM is, big endian or little endian. Okay, you can ask ChatGPT. It will tell you. I think that is probably little endian, because this. Yeah, I mean this has been made popular by this architecture. I mean, you could say it's a bit. I mean, it's probably unfair to the Indians, because the Indians are so many. Yeah, and they thrive on the. I'm always confusing this. So the Indians thrive on the left, right, side of the road. So, but almost everybody else in the world thrives on the other side of the road. So this is much more common to thrive the way that here in continental Europe thrive. Yeah, I mean around the globe there's England, then there is, you know, the Indian, Pakistani, and so on, and then there's Australia. So that's, you know, and of course South Africa, Namibia, yeah, these things. But I think that the little endian has become more common. So one thing is, before Apple changed their processors a lot of times. Yeah. So now they have their M12 chips. Previously they were using x86, and if you're old enough like me, you remember that they had something that was based on this Motorola architecture, which then was big endian. And this actually causes a lot of trouble, because now all your numbers are in a in a different format. I mean, it's nice if you're sticking to Apple all the time, but for example, if you want to run Windows on Apple with the old Apples with an emulator, what they need to do is every time they touch data, they have to turn it around. Yeah, which makes life very, very complicated. Yeah. So, yes. So big endian and little endian. A little bit the trouble is that this is also applying to this, what we call the lane in this vector. So when we initialize a vector with data like this, so in the first place, we put the lowest lane, as we say. So the lane is the place in the vector. Then we put this here in this x86 vectors, and I mean this here is just for this big endian is just here for comparison. This AVX only exists in this kind of processor, so they were always using little endian notation. So they will put what you put in the front of the arguments, they will put in the end of the vector. And what you put in the end of the arguments, they will put in the beginning of the vector. Yeah? So you need to be aware of this, because if you load an array that's already in the right order, and you just load it by the load statements, then the first thing in the array will be put here, and the last one will be put there. So when you hand fill, so it means when you hand fill your vector, it will be in the opposite way as if you fill it by reading the entire array. Is this confusing? Please.
Does it mean that when you store an array, like the next address is actually the one before or something like
No,
that?
if you store it, so the address runs from left to right here. Yeah? Even in little endian.
Oh.
Yeah, so the address runs. So this is you will count the address in a. So by the way, we had this in this example. So we are counting this up here with I. Yeah. So if we are counting upward, so this here has the higher address than this one. But when we hand fill, so when we call the function, set, as with hand filling this array. So I'm now hand filling this vector with 1, 2, 3, 4, 5, 6, 7, 8. So it will put this here, the first one, in the end of the array. So when I recast this to an integer vector and then I print it, then in P0 I will have 8. And in P1 I will have 7 and so on. Yeah? So it's the other way around. In principle, you don't need to care about this because they thought about this and have a function that sets the array in reverse order. Yeah? So, but then this is indicated here by, not by set, but by set R. So you have to indicate that you want to do it in reverse order, where reverse order is the order that I would naturally think is the right, maybe this R is not for reverse, but for the right order. I don't know. Okay? So, I think that all of this was, I mean, Intel is selling compilers. They didn't necessarily want this to be a very nicely readable format, I believe. Okay, so what we are now going to do is trying to get this to implement something along this line. So am I still? Let me see whether, because it's always asking for the. Okay, I'm apparently still. I don't know why it's asking for the password while I'm in it. Okay, so now what we are going to do is, so you can pick up this file at lecture 9, matrix multiply. Yeah, please also take the job file and copy this into your own folder. So here we are defining a matrix size of 512 in this case. I have a function that prints this matrix. That's not so important. And then here I have a main function. Okay, here we are going to allocate memory. I guess I have to go through because we have not talked about allocation, I believe, so far. So let me briefly go back to our to this very basic challenge. Yeah. So by the way, nowadays they build computers only for matrix multiplication because matrix multiplication is what is happening in artificial intelligence. Yeah. So this is why this has become very common to implement these. So okay, we get a matrix A and we get a matrix B and we want to get out a matrix C. Yeah, and this now can be written. So the function that you have to implement is Cij is the sum over k from 1 to n aik times bkj. We are assuming that this is a square matrix, so it's n by n. And yes, so we put this in this order. So I times n is the row and j is the column, and then we simply have to implement this function here. Okay, so I was a little bit ahead of myself because I actually wanted to go to when I opened the code, because now we want to briefly talk about allocation of memory. So what you may find inconvenient in C is that if you want to define an array, then you always have to know the size of the array at compile time. Yeah? So why is this the case? So in other languages, so Python or even Java, you make an array, so you can have a variable, you can first calculate the size that you need, and then you get your array of that size. So why is this a problem for C? Any idea? So C does not manage the memory for you. So you have to care about your own memory. Of course, there are libraries and classes that take care of your memory. So this is, for example, in the standard library, you can define a vector with a variable length. So this vector, this needs to be, called with new, and later it has to be destroyed. Yeah, but otherwise it takes care about its memory kind of itself. But for this you already have to use the standard library. It's not an intrinsic functionality of C itself. The reason is that, of course, memory has to be managed, and the way memory is managed by the operating system is that there is two places, roughly, where you can put up new variables, namely the stack and the heap. So all the primitive variables, so when you make integer something, for example, let's go through this. You have this int star. So this is now the pointer to A, which you then have to allocate. So A would be a matrix. So if you generate a variable like this, this will be generated on the so-called stack. So what is the stack? So you all heard about Stack Overflow. This is where you get the answers, or where I may get my answers, or how I should go prepare my lectures. So the stack is a place. The stack actually in memory is a place where you put all your variables that you generate like this, where you have a known size. So by telling the compiler that this is a pointer to an integer, it knows what size this thing has, because it's only the pointer, it's not the matrix. So this is the address of the matrix. And depending on whether you have what is your operating system, if you're 32-bit, 64-bit, this will be either this pointer will be 32-bit or 64-bit of size. So now this, once it is generated, it is put on the stack. So the stack is a place in the memory where you can put something, and then you have a stack kind of counter. So you know where you can put the next thing, because you know the size of the thing that you put on the stack. You can, if you want to introduce a new variable, you can put this again on the stack, and the stack is growing up. So in this example, what is going to happen is the first variable that you produce is this r star. So this will be on the low end of the stack. Then you do an allocation, this comes later, and then you call this function print matrix. So when you call the function print matrix, what a function call does, as long as it is not inlined by the compiler, what it does is it takes the arguments of this function and makes here, because they are passed by value, right? So they will make a copy. Passing by value they make a copy of these variables, and it will put them on the stack. So this here was the one that was generated here. Then when we call this, this comes in here as matrix, the pointer to matrix. So actually, these two things point to the same thing, yeah. But they will on the stack, they will be there twice, yeah. Because this here is from the main function, and the second one here comes from the arguments of the function. So it has here. I'm not sure. Maybe C orders them in the opposite order because they are. I don't know, but they will put these three arguments one after the other on the stack. Yeah. So rows, columns, they will be on the stack. And then we get into the loop, and then here is again we have a new variable in the scope. This is this integer I. This will be put on the stack next, and then we go into the second loop, and we'll have this second variable j on the stack. So the stack is useful because it works together with the scoping that we use here in C and C++. So you're all aware what scoping means. Okay, 30% nodding. Yeah, so scoping, so for example, the scope of this J, this is the iterator for this loop here. So this will have its scope within these curl brackets. Yeah, so the curl brackets always define a scope in C-like languages. Yeah, so would be the same in Java, for example. So in here exists J. And because we are always opening brackets, so the last bracket we are closing, when we close a bracket, we are always closing the last bracket that we opened. Yeah? And so you see this works together with the stack, because the last thing that we put on the stack here was the J. So this is on the top of the stack. So once we are done with this loop and J goes out of scope, this here will be cleared from the stack. Yeah? And next thing is when we go out of that loop, this here will be go out of scope. And when we finish the function, then also the arguments of the function go out of scope. Yeah? So by this scoping mechanism, we have a way of holding our variables in a consistent way. So we are never pulling something out of the stack somewhere in between, but we always put something on top of the stack and we remove something from the top of the stack. So this requires us to know beforehand how large things are. Yeah, so we can only put things on the stack when we know how large they are. And we can only remove stuff from the stack when we know how large they are. So this means we cannot put everything on the stack, and this is where allocation comes into play. So on top of the stack, we also have something that's called the heap. Yeah, so this is a big place in memory. There could also be different places in memory that are kind of dealt with the operating system. So when we need more memory or more space than we can handle on the stack, what we do is we ask the operating system to give us this chunk of memory of a given size in which we can store our data. and then we have to address. So then we have to work with this. So we have reserved this place in our faraway memory. Then we can work with this. And once we are done with it, we have to explicitly tell the operating system that we want to get rid of this, so that it's now free. We return it to the operating system. Yeah. So in the stack, we don't need to do this. It's running out of scope. It's gone. Yeah. So we never need to destroy here this variable I, but we have to destroy this thing here. Otherwise, it's not returned. So, and if you don't do this, you wouldn't notice anything strange for a very long time, yeah, and then suddenly you would notice that your computer suddenly runs out of memory. And you observe this. I mean, this is a very common problem with serious programmers, because you see, in commercial software, yeah, if you run them too long, they will catch up more and more and more and more memory, yeah, because they are not cleanly programmed. They somehow have a memory leak. I even found the memory leak in some integrated programming languages. Yeah, so an interpreter can also have a memory leak. So that you try to clear something, but memory is not getting smaller. Yeah, so somewhere they forgot to clear their memory. So now in C this works like this: memory allocation. So malloc. Yeah. So you have to. I want to get the address. I ask the operating system for the address of my memory, and I have to tell the operating system how much space it is supposed to give me. So what I'm doing here is I have a matrix of the size n times n, and here I'm just telling very bluntly how many bytes this memory is supposed to be. So I have to explicitly tell it that I want to store integers here. So what I have to do is I have to ask what is the size of an integer. And I actually have to ask this because depending on my machine, an integer may have different size. So usually it will have 4 bytes, but it could also have 8 bytes. Yeah? Okay, so this is how I allocate the stuff, and then later I have to call free in order to get rid of free it for the operating system. Okay, I do this. Okay, maybe I go through the slides and then we go to the example later. Yeah, so in principle, your compiler could use this extension itself as long as you allow it. I mean, compile it with the appropriate flags. Yeah, but this may not actually happen. Usually, it wouldn't. In my opinion, this is my personal opinion, these instructions are pretty cryptic, yeah, not easy to read code. We have no branching. I'll later come to an example how we could simulate branching, yeah, but we don't have branching in vector operations. This is a typical problem of all as single instruction multiple data. Now, of course, doing this may also increase the power consumption, and because computers nowadays clock down when they get hot, they may not actually get faster. Okay, so some downsides, and now, okay, we'll do this later with the branching. And now come actually to the, hopefully to the example.
I think
The
the server is ambitious.
server is,
But I think I did crash it.
you crashed it. Okay, you know that this is on the recording. Oh,
Okay, it was really good.
okay, I have to admit, that you cannot log in.
Yeah.
Okay, so you can log. So but you don't, please don't crash the login. We have only one login node left. Yeah, I logged in with the actual IP address, but I don't think this makes a big difference. Okay, let's go through these things here again. So what I did. So do you understand what this here means? Define N512. Can you explain what this means? I mean, this is like extremely old-fashioned. Please.
Maybe it's just the count of elements of the whole matrix.
Yeah. Okay. No. Yes. So N is the size of the matrix. Yeah. This was not what I meant. I mean, this way of writing it down. Yeah. Right. So we define this as a macro, which means that this N. So compared to setting a variable, this N is known at compile time. Yeah, so I could also set it as const, then it would also be known at compile time. So this is a little bit old-fashioned, but I'm an old-fashioned guy. I like old-fashioned stuff. By the way, this here is also, this writing out routine is also an old-fashioned style. Yeah, maybe nowadays we would do this a little bit differently. Okay, see, we are now, that doesn't really matter that much, but we are using integer matrix. We do integer matrix multiplication, which is a little bit unusual, yeah, but you can replace all the integers with floating points and then you get to the same, basically doing the same. So, we need, so for everything that we get on the heap, we need a pointer. Yeah, we need an address to storing the address of this. So we'll have the pointers to the matrix A, B, and C. So we multiply A times B equals C. And here we allocate this memory. So we cast this into a pointer to integer. And we do a memory allocation of n times size integer. So then, in order so that we have something to calculate, we initialize this with a random value, yeah, using this. So we set srun 0, and then we go through the entire matrix and initialize everything with this random value. Now, important thing is, this is of course a pseudo random value, so you cannot. So, yes, I mean, I should potentially ask you. So, how do you actually generate random values in a deterministic computer? So these things are called pseudo-random numbers. Yeah. So there is a deterministic procedure that somehow produces these numbers, and they need to have a starting values from which they generate these random numbers. and this is, so they need a seed. So when you want to have really the random numbers, what you could do is you could use the time as a seed, because this is something that's changing all the time, right? Then you will always have different pseudo-random numbers. If you want to have the same random numbers, you will give a fixed seed. For example, here I set it to 0. Then, as long as I use the same compiler and run it on the same machine, I will always get the same random numbers. If I run this on a different compiler, I will get different random numbers, but I will have consistency between my results when I run them multiple times here. Yeah? So this is important in order to see whether we are actually doing the right thing. Okay, so we fill these things. Here we do integer division by 10. Then we start. So now this is a little bit more modern way of writing things. So here I have to admit these things are all prepared by former colleagues of mine. So they use here auto instead of using a long. Yeah, I guess this would be a long. So auto is if you don't care about, if you don't want if you don't like to remember what are the types of your function, and you put here auto, then this is using calling a function. The function has a return value, so it can determine from the return value what type this would be. Yeah, so you can always write auto. So, and then you do these matrix multiplication. Yeah, so you initialize this here by 0, and then you will add things here up, and then you take the time. Okay, what you do here is you take the time first, then you take the time afterwards, then you print the matrix, and then you write out the runtime. You see, this is funny what this guy did. So here, up there, he's using the old C-style printf, and here he's using the stream. So this is a more modern way of doing the same thing. So you've seen both, yeah? You can combination of both. This is maybe what we call legacy code. So by the way, there is now a lot of talking about we should always use Python. Yeah. One thing that you should know about Python is that it's a very unstable language in the sense that it's always changing, and it's not backward compatible. So the code that you wrote 5 years ago may not run nowadays. Of course, this doesn't matter because it's a scripting language, and in a scripting language, you write throwaway code. Yeah? So you run your code once and then you throw it away, and you're not interested in 5 years. Then you write a new code. C is, so all the operating systems and all the standard software is written in C, and this for the last 50 years. And even in modern operating systems, there's still code left that is 30 years old. And therefore, it's very important for C that that you can still run or compile the code that you have written 30 years ago. This works with C. There's no way on earth this works with Python. Yeah? So here, this is old-fashioned code, how you would write this 30 years, 40 years ago, you would write it exactly like this, and here you would write it 20 years ago. Yeah, and maybe now there's okay. So I don't think that they changed it a lot in the last 20 years. This one, but you can. There's of course always something new here, but you can still run the old code because in long-running software projects, the old code is still there, and it may be the most valuable thing because it's well tested. The guy who wrote it is dead. You can't ask them, and nobody knows what it's doing, but it's running, so it's important. Okay. Having said this, we are going to do, we do something else first. We go to that folder, CD PVR 2025. So that's mine, so it's Gaia, and it will be lecture, capital lecture, lecture 9. So I have put there a job file, yeah, because I noticed I'm not using job files enough. So we are going. So I had some problems with the. What is it? Do I have it in my memory? Yes. So. Okay, I have, yes, S info. So I had in the past, when I wanted to do this in the lecture, we had some problems that it would not start, right? So because we basically, actually here in teaching, when we write S info, so we see what nodes are idle, and what we have here are the queues. Yeah. So in principle, we should use the teaching queue, but the teaching queue is somehow dead. Even though there is an idle, there's something idle. I believe it doesn't work. Okay, we give it a try whether it works. So I don't want to, let me put here. So in this, you have to give the partition. So where you want to write it, run it. So I'll try to, I'm not sure that this works. Okay, I'll put it to teaching. I'll now saving this. What I have down here, so I'm using one node. I mean, more than one node I wouldn't get in teaching anyway, because there's only one. And n tasks per node would be 4. So this is how much it would use in MPI. Even though I don't use MPI, I just started with MPI because MPI can also run normal processors, normal, say, programs. Yeah. So and I called it mat. So what I did before is I compile with G++ matrix into this thing mat. Yeah. So I guess I saved this, and let's see whether the teaching queue is actually working. S-batch job file. So it has submitted something. So actually this is supposed to run only a few seconds. Yeah. And we don't see any Oh, it actually ran, that's good. So we can open, why don't I see it? Core slurm out. Oh. Process run 3. Okay, so this crash, okay, so this crashed it. This is why we have these core data, because these core files, because something was wrong. So it actually didn't run. Question is, why didn't it run? Okay, what I did before and what, let me short run small. Okay, so for example, I don't know whether this is the reason, but let's try it. Yeah. So because we always have short runs, short run large, small train, alloc node train. Are there any that are idle? I don't see it. Okay, let's go to, it was actually running. I don't know whether the problem that we had here was due to that being, I think they have different processors on the teaching, so because these are older computers, yeah. So therefore, what so I'm not sure that it didn't run because there was a mistake or that there's a problem with these nodes. So for this reason, I will now put it into short run small. Yeah, I think this should be okay, because this, the only problem that we may have is that the short runs are occupied. I'm always too stupid to dispatch. Let's cancel this control. 375. Do we get any information? Submit time. Oh, okay, we get an output. Okay, so you see, unfortunately, the teaching nodes that we are supposed to use, they are broken. So they run the program, but they crash. Okay, so now I run it on this, on the short run node, and then I actually get an output. So yes, okay. Okay, so that's kind of very bad, because what I did is, because I run it in MPI, it ran it 3 times. It should actually run it 4 times. I don't know why there's only 3 of them. So because I did not distinguish between the, but anyway, so the time that it took was 1 second, yeah? And it kind of ran, so what I should do actually for the time being in my job file, and you should do the same thing in your job file, is number of tasks per node. As long as we are using only 1 task, we should also set this to 1. Then doing the SBatch job file, and then we have a new job with the job ID 8736. Let me see. Okay, it's already out. Okay, now we printed the matrix only once. At least this is what it says here, yeah? And it's still very long. So, okay, timing was the same, yeah? Because all that we did is previously we did 3 times the same, because as you notice, there are no MPI instructions in this in this example. Okay, so now can this here go out of the way? My God. So, okay, I have the wrong. So what we are going to do now is to make a copy of this. Then we paste it here. Now this is called copy. Now I'm doing rename. And instead of copy, I call it AVX. Okay? So, now we try to make this AVX style. So, since this is not my profession, I now rely heavily on my cheat sheet, I believe. So, first thing that we have to do when we want to run with AVX is we have to include the header for the intrinsics. Yeah? So we have to. The trouble with having 2 keyboards in front of me. So we do an include. Yeah. So you can type with me if you like. So there's these intrinsic are, I don't know why this is called like this, intrin, yeah, I don't know why it's called this way, but this is the one that we want. So now we're including this one in order to actually do our intrinsics. Then we keep all of this stuff the same. We do the initialization the same. And then we have here this thing here. What I'm going to do is I'm going to copy this, paste it here, and say this is AVX now, and the other part, so this loop, I will use control, so I'll turn this away. Yeah? So now in this loop, we need to do the vectorization. So in general, what we do when we use vector operations, instead of the loop, we'll parallelize the innermost loop. Yeah, it's difficult. I mean, okay, so there may be if you do domain decomposition, yeah, on different computers, you will divide the outermost loop. But when you do vector parallelization, you divide the innermost loop. So basically, we'll be in this loop over K. This is the way. This is where we have to do our operations. So we have to get an integer M256 integer. Now I'm relying on my cheat sheet, as I said. So yeah, so we can Okay, I see. So maybe I was a little bit lazy when I said this gives no indication here. So basically, if we don't indicate what it is, it will assume it's a flow, because this is what you do matrix operations on. So if we want to have our vector as being integer, then we'll put an I here. Yeah. Where are we? So we need to kind of capture our result, and I'll put this into some vector which I initialize with zeros. 5, 6, set 0, and this I do for signed integer. 256. So, because I'm calculating a sum, so I'm summing stuff up, and I now initialize. I'm going to initialize these things with 0. Now this is similar to what we did here, right? With the C. So I'll going to, here we set the C value in this position first to 0, and then I sum it up. Yeah. So I replace this by this sum vector. Okay. Let's get rid of this. And then I have to sum over this k. And now what I do with this k is I'm going in steps of 8. Yeah, because I have 8 integers in one of these vectors. So then I have to stop early enough. This means I have to stop before I'm at the end of this. And I have to, I'm in the wrong place. I want it to be here. So I have to stop before we get to the end. And here in this k, I use k plus 8. So I'm updating by 8 each time. So, and now inside this, I have to do my sum. Yeah, so that is I have to replace this. But before I can do this, I have to load my vectors. So I'm starting with my A vector. So I do underscore M2 5, 6. So it's an integer, therefore it's coming as integer. And I call this now my A vector. And this is now loaded MM256 load. So now we said we can do an aligned load or an unaligned load. So in order to do an aligned load, we need to be sure that the matrix starts at the right address, which we could in principle do by looking what address we got and then shifting it so that it starts by the right address. But since now I'm lazy and I don't want to do this, I tell them I don't know, and we load it unaligned. Okay? So then what we do, what we load is a signed integer. Here again, this 256. And now we have to load this from this position here. Yeah, so we get actually this is what we want. Yeah, so I put this into here, but I need to get the address of this, and then I also have to cast this, because this is now integer. I have to cast this into the type M256 integer. Yeah, so this is, I have to cast this pointer. Yeah, so I have to cast this into such a pointer. So, and then I have, of course, to do a semicolon. So now I loaded my A vector. I could do this so easily because, as you see, A is aligned in this way that you simply count this upward. Yeah, so we're iterating over K. So we are increasing K here. So they are one after the other. Our B vector, unfortunately, yeah, if you think about matrix operations, now this was a row, now comes a column. Yeah, so this goes. That these things are not aligned. So they have to be read in an individual fashion. So there is the possibility to use a gather function where we give a map of coordinates and gather them this way. The way it's written on my cheat sheet is different, so I do it in a different way. Yeah, so here what I do is I use the set function that we have introduced and read the stuff one after the other. Yeah, so this, I mean, in a sense, this is similar, because otherwise I would have to make the map first, and then I have to read the map. I'm not sure which one would be faster, but maybe as a homework you can try this out. So we do this here again. So this is with small lowercase b vector is equal to, now we use the MM256 set. EP, I'm actually not sure what EP packed integer, okay, I'm 32. So this is the function for setting. So now you see there is no reverse here. We can try out reverse later, but since there is no reverse, we have to go through this backward, right? So what we have is this guy. And now we have to fill in this 8 out of this. So this K, so we have, as I said, we have to do this backwards. So this K, now what am I doing? Okay, I need this 8 times, but this K is now not the K, but the K plus 7. Yeah? And this here is the K plus, okay, saving some time. This guy cannot use an, okay. So this is K plus 6. K plus 5, K plus 4, k plus 3. You help me counting, right? K plus 2, k plus 1, and then we also have k plus nothing. So now we have read them in their strange order. Okay, so obviously I made a stupid mistake up here. So you should always tell me, yeah? This is an underscore. So now we can do our summation, and instead of putting this in C, we put this into sum vec. Yes, now comes the actual operation. So this is M 265, 256. Yeah. So we do a multiplication. So I'm doing that stupid example where I multiply two integers. When I multiply two integers, the result is twice the size. So this would actually give me this would result actually in 4 longs rather than 8 in single size integers. Yeah. So in order to get only the 32-bit version, I have to tell it that we do multiplication only of the lower part. For integers, EPI, integer 32. Yeah, so by the way, you see we can also have this in 16 and 64, but we now want to have it in 32. So, and what we do is we do the A vector and the B vector. So, by the way, I made a mistake. I made a mistake. This is not the sum. This is first the product. I need to have M. I need a new variable here. M256 I, and I call this product. So because okay, product. Let's call it product. You have to take care about the capital, non-capital things. Okay, so because first we multiply these things. But when we multiply, we are not done yet. We also have to add these together. And so we have to accumulate them. Yeah, so we want to accumulate them. And this is, therefore we need another line. We have to write, how did I call it? SUMVEC, yeah. SUMVEC. So here we accumulate the stuff by using the M. So you see, this is only one. You see, it's not, you don't have these easy operators plus equal, yeah? So that's not how it works, yeah? So you actually have to write that we do the MM256 add and that we do this on integers, and that we use the stuff where we want to add it to, yeah. So we have to write, and the stuff that we just calculated, this product. So then we got this accumulation. Okay, so then we got this accumulation, and then I guess we are done with this. So now we have everything in this vector. Now we have everything in this vector. And we actually want to wait. So we still need to get this into. Maybe I should not have. What did I do? Okay, so what we have done? We've been here, yeah. So in this. We are going over K, and actually we want to sum things in K, right? But so far we have not accumulated the entire stuff, but we have only added it in the vector. So now we have a vector of 8 parts, and we have to put this part. We have to sum over this vector, which unfortunately is not implemented in AVX. So like you would imagine, they'll give me a sum of a vector, that there is a function, but apparently there's no such function. Yeah, so we have to write this ourselves. So summing over the vector. So for example, what we could do is we take we had this as integers, right? All of them as just integer, yes. So integer, okay, temp 8. So we have this integer, and we want now to put this vector back into this array of integers, of 8 integers. So for this, we use the store function. So this is MM256 store. So we don't know whether it's aligned or not aligned, so I assume it's not aligned. We want to store signed integers 256 again. So we use we cast our integer to an I always write this in capital. We cast, so when this is an integer, right? A pointer to an integer array. I mean, an array is always a pointer to the first element. So, and now this expects a pointer to a vector of this kind. So we'll cast this into that particular pointer, and here said, so we cast the address to what we are expecting here, and then we add here this what we wanted to actually store, which is the sum vector. So now what do we have? We have now the vector again as an array with these 9 entries. And these we have to sum up by hand. So, by the way, okay, maybe I should not delete this. Let me take this out, and we have this here. We set this to 0, and now we oh no, this is okay, no, that should work. So we add C. Okay, I have to write it correctly. So this is what we had previously. Yeah, we are adding to C. We are adding the sum. Now we have, since we computed the sum. Now, since we computed the sum up to the point that we still have it in this vector format, we add it to this. We initialize it by 0. Then we do this calculation, and now we can add this. And the way we add it is we have to, add all of them by hand. So we do this. This doesn't look very efficient, but yeah. Okay, now we have all of them in there. Okay, so I'm going to save this. I think we are in principle done. Do you see any questions? Any things that I've forgotten? Any small blah, because otherwise I'm going to compile this. Now I'm so stupid that I have to look up this. This is AVX, right. Okay, so what we are going to do, we use G plus. We are using G++ minus MAVX2 matrix multiply AVX minus O, and I'm taking the liberty to put this into the same file, yeah, overwrite my previous file so that I can just run the job file again. Yeah. Okay. Did not complain. As batch job file. So we got a new handle. It's the question whether we got also a result. Not yet. You know, this is not good for lectures. Yeah. Okay, so now we do what you're not supposed to do. Okay. Waiting. Okay, so that's our result. So why is this so large? Yeah. Okay, 0.5 seconds. So what was the previous one? I guess this one, right? So it is twice as fast. You may have hoped that it is four times as fast or 8 times, but it's not. Now, other question is, did it give the same? Did it give us the same results? Okay. Now is the question whether they are in the same. So how do I know whether we got the same results? By okay, let me say that this is the last number, 10,301. I have no idea what we do when I get a different result. Oh, we did not get the same result. So why didn't we get the same result? Because I made a mistake, obviously. Okay. 0, 1, 2, 3, 4, 5, 6, 7, 8, 7. Yeah, so we got. Okay, so one thing that we should, in principle, take care of is, even though I think this is not the, 512 can be divided by 8, right? So that should not be a problem, but in principle it is a problem that you may here run out of, if this is not divisible by 8, so we'll chop off the rest of the line. So what we would actually need to do is to take this thing here out. Should put this actually to the outside. So we can leave this here empty. That's ugly but useful. And then when we are not done here, we should do the rest in the usual fashion. So let me see. We still have this here. So the thing is, we are starting from the previous k. So do you understand what I'm doing here? So this previous loop, yeah, would terminate if it's not divisible by 8. So it will terminate early. So it will not go to the end of the matrix by summing. So we would have to get the rest of it the usual way. Yeah? So let me see this. So at least I am now expecting that it does not change from the last version that we looked at. For something that takes only half a second, that runs very, very slowly, right? Okay, now we have it. So, because it's not doing anything, it should, okay, the loop should not do anything, so it should be done. So it's the same number that we had. Okay, let me try one thing. Let me try one thing out. So for example, if we simply summing over the vector. So, okay, not to be confused, I will eliminate this now. So now there will be no AVX working. So this will, start from k equal to 0. So we should be able to see this. So we get 85 here. Now we have 85 done. Now we are expecting to have this in 1 second. Yes, one second, and oops. So what was here my output? No, it's the same. Okay, I don't know what we were looking on before, but this is the same. Now using AVX and not using it gave the same result. Okay, so I don't know what we were looking at before. Yeah. Okay, so basically, okay, so I took a little bit overtime with the lecture now. There is actually as of your exercise now, load store instruct. Okay, I still have to. Okay, so there's one point that was not in this example that I want to address here, namely the branching. Yeah, obviously in single instruction multiple data, there is no intrinsic way to branch operations, but there is a way to simulate this by using masking. So branching means you want to apply one operation to one part of the vector and not to another part of the vector. So in single instruction multiple data, you always have to go through both branches, one after the other, but you can mute the operation in certain places of the vector. So in this, if something here is larger than the other, do result is the sum, or else do something else. Yeah. So you have to go through both of these things. So what you need to do, so okay, you set these values, then what you need is a mask, and you generate this mask here because this question was whether this here is larger than that. So you use compare greater than. Yeah, compare greater than. So there are other compares. So this will generate a mask that now you can use in these operations. So you do the one operation, you do the then branch by computing everything for then. Then you do the else branch, so the then is plus, the else is minus. Yeah, so you have done both computation, and then you do a blending of both, yeah, by using this MM256 blend, where you have the else branch, the then branch, and the mask that will decide whether you get the one from the one vector or the one from the other one from the other vector. In this way, you can simulate branching in AVX. Yeah? And this is always a problem. We'll also see next week with CUDA. This is always a problem with single instruction, multiple data. So, now we are in principle done with the lecture and come to the exercise, where you should actually now use the code that we just wrote. I don't know whether you followed this. And in addition to using AVX, we want also to use MPI. So MPI and AVX together. Yeah? So, and if you have no AVX, you can also do just MPI. Yeah, this is so. But this is what we call heterogeneous parallelization. So you parallelize on different layers. So the way we would parallelize in MPI matrix operation would be as follows. So we would like to have the data as close together as would be possible. So we split up the A matrices because then what we can do then, if we have here a smaller matrix, fewer columns, fewer lines multiplied by B, so we would, this A1 multiplied by B would give us C1. And A2 multiplied by B would give us C2. Yeah? So then this would be the natural way of splitting up this problem. So we'll have here different ranks. So what we need to do is we have to broadcast, so we generate this matrix B, then we broadcast it to all our ranks. So because this is something that we need everywhere. We scatter the different parts of A to the different ranks. Then we do the local calculations, and then in the end we gather this back to rank 0 and do the output. Yeah, so this is the idea, and now this is for these different functions here, MPI bcast. So this takes the buffer, how much we have to send, data type as usual, and this root. So I've written this maybe in a different, in an unusual form. So root can be any of the ranks that exist. So what we usually do is we put root to 0, that the 0 rank is the one that is distributing stuff, and all the others are just receiving it. Yeah, but it could be any other. So the root is sending stuff off, and everybody else is getting it by calling the same function. So then if my rank is equal to root, this is a sending function. If my rank is not equal to root, this is a receiving function. Yeah? So this is how broadcast works. So scatter takes the data at the root and distributes different parts of this to to the different processes. So this would be now this smaller matrix. So we have the send buffer, which is the entire thing. The send count. So, okay, the send count is the entire data. Yeah? Because here we have a send count and a receive count. Because we send out everything and then each part of this just receives part of this. Yeah, so it needs a receive count. And this goes to also a receive buffer that may be different. I mean, this is different from the send buffer. Right. And the last thing is the inverse of this, yeah, where we gather our information. We send our send buffer back with a send count, and there again is a receive count, and this will end up in this receive buffer. So I guess that's it what I wanted to say. And now, yeah, my hope, we have like potentially an hour. So my hope was then that you use these three. I may keep this here. That you use the file that we generated and implement this together with MPI. And for this, I will stop the recording.